Today we will start a new chapter. So, introduction to semi groups and applications to evolution equations. So, the theory of semi-groups plays an important role in the study of evolution equations, and this is an abstract framework in which we can study many evolution equations. So, one of the essential ingredients of this theory is the notion of an unbounded linear operator. So, first we will talk about unbounded linear operators. Okay, so we start with so we take V and W Banach spaces, and D of A is a subspace of V, and A from dA into W, so this is contained in V into W, a linear map. So, a linear operator will henceforth be of this kind, namely it is defined on a subspace of V, not necessarily on the whole of V, and it is a linear map. So, then D of A is called the domain of A contained in V, then image of A, so this is equal to the range of A, and this will be denoted by R of A, which will be contained in W. Then N of A is the null space kernel of A. So, this will be set of all x in V such that Ax x in D of A such that A of x equal to 0. So, this is called the null space of A. Okay. And so, now we have the following definition. Okay, a linear operator A from D of A contained in V taking values in W is said to be bounded if there exists a C greater than 0 such that for every U in D of A you have norm AU in W is less than C times norm U. So, this is the usual boundedness which we have seen in case of linear operators. Otherwise, so if this is not true, it is said to be unbounded. Okay. So, it is said to be densely defined if D of A closure equal to V. That means if the domain is dense. So, that is just this thing, and it is said to be the graph of A equal to G of A. This is equal to set of all x, y in V cross W, x in D of A and y equals Ax. Okay. So, and then A is said to be closed if G of A is closed in V cross W. So, remark, so if dA equal to V and A bounded, then that is A is a continuous linear operator, as we have usually know in functional analysis. So, in general, a bounded linear operator extends uniquely to a continuous linear operator on dA closure. Okay. So, if A is closed, that means the graph of A is closed and dA equal to V, then this implies that A is a continuous linear operator. This is nothing but the closed graph theorem, one of the famous theorems in Banach space theory. Now, A closed implies N of A is a closed subspace of V. Check. Very easy to check. So, normally if you have a continuous linear operator, then of course null space is a closed subspace, but if it is a general linear operator, nothing can be said about the null space. If A is a closed operator, that means the graph is closed, then you say that it is a then the null space will be closed. Okay. So, then remark how to check A is closed. So, what is the method which we usually employ to this? So, we want to show GA is closed. So, you take UN in D of A and A of UN belongs to range of A, of course. So, that UN D of AN, AUN belongs to G of A. So, assume UN goes to U, AUN goes to V, this is in V, this is in W, and show that 1 U belongs to D of A and 2 AU equals V. Then GA is closed. So, this is the method we will always follow, okay, because if you take UN in the product space, UN AUN goes to U of UV. So, we want to show that UV is in the graph also. So, U must be first of all in the domain of A and AU must be equal to B, and that is precisely saying that the graph is closed. So, this is how we prove that the graph is closed. So, that is, so almost all the operators which we will come across in course of the next few lectures will be of course closed and densely defined. So, anyway, let us start with some examples. So, example 1. So, let omega equal to 0 1 contained in R and V equals W equals L2 of omega. Okay. So, then you define D of A equals H10 of omega, and for all U in D of A, AU equals U dash, namely the distribution derivative. Okay. So, then it is well defined. Okay. It is not defined on all of L2, it is defined this way. So, then A is densely defined, because you know that D of omega is dense in H10 of omega and D of omega is dense in L2 of omega also. So, H10 of omega is dense in L2 of omega. So, A is densely defined. Then it is unbounded. Okay. So, let us take un of x equals root 2 by n pi sin n pi x. Okay. So, then un dash of x is nothing but root 2 cos n pi x. Okay. And now you have, so this is equal to AUN. So, mod un 0 omega, this is the L2 norm. So, this is equal to 1 over n pi, and that goes to 0 as n tends to infinity. Whereas mod AUN 0 omega is root 2 cos n pi x, and that we can easily check. This is equal to 1 for all n. So, you cannot have a constant AUN less than C times UN, because this stays at 1 and this goes to 0. Therefore, this implies that it is unbounded. Now, n of A equals set of all u in H1 0 such that u dash equal to 0. Therefore, by Poincaré's inequality implies that u equal to 0. Okay, you know that u dash mod u dash L2 norm of u dash is a norm and in H1 0 of omega. Therefore, by Poincaré's inequality is 0. So, n of A is strictly 0. Now, what about the range of A? So, range of A, so if you have u dash for u in H1 0 of omega, this implies that integral 0 to 1 u dash t dt is u of 1 minus u of 0, which is equal to 0. Okay. Conversely, if integral u v of t dt equal to 0, then you define u of x as integral 0 to x v of x, v of t dt, then this implies that v is in H1 0 of omega, okay, and u dash equal to b, okay, and therefore range of A is set of all v in L2 of omega such that integral 0 to 1 v of t dt equal to 0. Finally, we want to show that A is closed. So, let un go to u in L2 of omega and AUN go to v in L2 of omega. That means un dash goes to v in L2 of omega. But this is one of the very first things we did when we proved Sobolev spaces, especially to show that it is complete. That means if un dash goes to v in L2 of omega and un goes to u in L2 omega, this implies that u is in L2 of omega and u dash equal to v, okay, and that is AU equal to v and u is in D of A, okay, and therefore you have that this is a closed operator as well. So, this is one example which we can. So, second example. So, again omega in Rn now, bounded open set of class C0, okay, and then again we take V equals W equals L2 of omega and I want to define of A. So, domain of A I have to first define. I am going to define this as H2 of omega intersection H1 0 of omega, and A of u is equal to Laplacian u in D of A. It is well defined because it is in H2, Laplacian will be in L2, and then I am just adding that it is in H1 0 of omega. So, again A is densely defined because H2 intersection H1 0 of omega contains D of omega, and which is itself dense in L2 of omega, and therefore D of A is dense in L2 of omega. Now, it is unbounded, A is unbounded. So, let Wn be eigenfunctions of minus Laplacian with Dirichlet boundary conditions. That means Wn belongs to D of A automatically, okay. And what is A of Wn? Which is minus lambda n Wn, okay, the corresponding eigenvalue. Now, mod Wn 0 omega is equal to 1, we know normalized eigenfunctions, whereas mod Awn 0 omega equals mod lambda n, and we know that that goes to infinity, and therefore this is clearly an unbounded operator. What about n of a? Again, n of a here is singleton 0, because if you have Laplacian u equal to 0 and u in h1 0 of omega, then Poincaré's inequality tells you that implies that u equal to 0. Okay. Now, if f is in L2 of omega, there exists unique u in h1 0 of omega such that minus Laplacian u equal to f and u equal to 0 on d omega. Okay, and so Laplacian u is minus f if you like. So for every f, minus f is okay. And regularity theorem, u omega is of class C0 and therefore implies that u is in h2 of omega also. So u belongs to d of a and au equals minus f, okay, and therefore range of a is the entire, it's an onto map, okay, it's the entire map which is full of things. So now a is again closed, so we have to show this, okay. So un belong to d of a, which is equal to h2 omega intersection h1 0 of omega, okay, and you so let Fn equals minus Laplacian un, which goes to f in L2 of omega. Okay, so we want to show that u, so un goes to u in L2 of omega. Okay, so we want to show this, but grad un square 1 omega is equal to integral mod grad un square on omega, which is equal to integral fn un, which is less than to mod fn 0 omega mod un 0 omega, and this is bounded. So un is bounded in h1 0. So un converges to u in weekly h1 0 omega week to some w, and therefore un converges to w in L2 of omega by the relic theorem, but un already converges to u in L2 of omega. So this implies that u is in h1 0 of omega and un converges to u weakly in h1 0 and strongly in L2. Now grad un, grad w for all w for all z in h1 0 of omega equals integral fn un fn z, and this implies that integral grad u grad z equals integral fz. So you have minus Laplacian u equal to f in omega, and by regularity you have u is in h2 of omega as well. And therefore minus Laplacian of un equals fn goes to f, which is equal to minus Laplacian of u, and this implies that a is closed. So these are two, in fact, very important examples which we will return to a little later on. So now I want to give a definition which is very important. So let us take a from dA contained in V going into W, which is densely defined. So this is a very important hypothesis at this moment. So let V star, W star are the duals of V, W respectively. So now I define D star equals set of all, so F, so define belong to W star such that there exists a C constant such that mod f of AU is less than to C times norm U in V for every U in D of A. So, let us assume that this is called D star. Okay. Now, then if f belongs to D star, then U going to f of AU is a continuous linear functional on D of A with norm V. But D of A is dense in V implies there exists a unique G in V star such that G of U equals f of AU for every U in D of A. Okay. So, we say D of A star equals D star and A star of f we call as G. Okay. So, then you have the G. So, A star f acting on U is equal to f acting on AU for every f in DA star and every U in D of A. So, at this juncture we will use the bracket notation. So, A star f U, so this is called the duality bracket from V star V. That means the first element is in V star and second element in V, and this is just this notation. So, this is equal to f of AU and this is from W star acting on W. Okay. So, we have this equation. So, this is the fundamental relationship which defines the adjoint operator. Okay. So, this is the definition of the, so A star is called the adjoint of A. So, theorem. So, we can define the adjoint only for densely defined operator because you need to extend it uniquely to the entire space, okay, using that definition. Okay. So, A dA contained in V going into W, densely defined linear operator, then A star from dA star contained in W star going into V star is closed. So, what A star, the dual adjoint mapping is always a closed mapping. So, proof. So, to show GA star is closed. So, let us take closed in W star cross V star. Okay. Okay. So, let us take Fn going to Fn in D of A star, Fn going to F in W star and A star Fn going to G in V star. So, what do we have to show? So, we have to show that F belongs to dA star and A star F equal to G. So, we have to show these two things. So, if U is in D of A, then what do you have? A star Fn of U is Fn of AU. So, this is in V star V, this is in W star W. Okay. But this implies, because A star Fn converges, so G of U V star V equals F AU. Okay. So, mod of F AU is less than or equal to norm G times norm U, because G is a continuous linear functional we know, and this implies that f belongs to dA star by definition. F of AU should be less than C times norm U, so we have that precisely this. And star implies G equals A star F, because A star FU equals FAU, equals FAU, but that is equal to GU. So, A star FU equals GU, but U is densely defined. So, that means the domain of A is dense, and therefore, two elements agree on a dense set, they have to agree everywhere. So, G equals A star F, and this implies that A star is closed. Theorem. Let A from V to W continuous linear operator. So, then it is obviously closed, because by the since the continuous linear operator graph is already closed. Therefore, then A star from W star to V star is a continuous linear operator, and norm of A is the same as norm of A star. So, proof. So, we have to show first of all the domain is the whole of W star. So, let F belong to W star, okay, and U in V arbitrary, okay. Then mod F AU is less than or equal to, so this is from W star to W, is less than or equal to norm F into norm AU, which is less than or equal to norm F into norm A times norm U, and therefore, this is some constant C, and this implies that F belongs to D of W star, A star, sorry. So, this implies that dA star equals W star. So, dA star equals W star, and therefore, A star is from W star to V star, and it is closed. That means its graph is closed, implies A star continuous by the closed graph theorem. Okay, and so you have F AU equals A star F U for all F in W star, for all U in V, and therefore you will have, so this implies check exercise, very simple exercise, that norm A equals norm A star. So, you just use this, take the modulus on either side and then take the inequalities, you will get norm A less than norm A star and norm A star less than or equal to norm A. Okay. So, now remark again, if V is a real Hilbert space, we can identify V with V star. We have already gone through this thing generally. So, if you take A from D of A contained in V going to V, okay, then we can define densely defined A star from dA star contained in V going to V. Okay, so you can just, the adjoint will also be defined in the same way, and so you will have A star U V equals U A star for all UAB, sorry, for all U in dA star V in DFA. Okay. So, definition A H, so V is a Hilbert space and A from D of A contained in V going to V densely defined. A is said to be symmetric if for every UV belonging to D of A, you have AUV equals VAU. So, this is just the inner product. I am just using the inner product here. So, since we are in Hilbert space, we can just use the inner product of the Hilbert space, okay, to the duality bracket is the same because as the inner product, because we have identified the dual space with the basic space, okay. So this is true, and self-adjoint if A equals A star, okay, that is D of A equals D of A star and A symmetric. So, if you have a continuous linear operator, then or a bounded linear operator, then there is no distinction between which is densely defined. So, it will automatically be a continuous linear operator, and therefore, the symmetry and self-adjointness are one and the same. But if you have a unbounded operator which is densely defined, then if you symmetry does not imply, so symmetry, so A unbounded, remark, symmetric only implies that D of A is contained in D of A star and that A star restricted to D of A is the same as A. Okay. So, to show that it is self-adjoint, that means you have to show that dA equals D of A star and A star equal to. Okay. So, symmetry is not alone enough. Okay. So, we will see examples of that adjoint next time.